Most rock-forming minerals are silicate minerals because about 84% of the Earth's crust is made up of oxygen and silicon. Although oxygen and silicon make up about 84% of the crust, their masses only account for about 75% of the crust, as shown in Figure A, because their masses are smaller than other elements like iron. A quick reminder that all minerals are crystalline solids, naturally occurring, inorganic, and have a definite chemical composition and chemical formula. Silicate minerals occur when silicon and oxygen are chemically bonded. Usually this bond extends to a metallic ion. Silicate minerals make up most of the Earth's mantle and over 90% of the crust. It is important to study the silicate minerals because we need to know the strengths and weaknesses of the ground we live and build structures such as our homes on. So the basic structural unit of this all silicate rock-forming minerals is the silicate tetrahedron. The blue atoms in the structure represent, in structure A, represent the oxygen atoms, and the center orange atom represents the silicon. The bonds that connect the atoms are covalent and ionic bonds. The simplest group of tetrahedra is the isolated tetrahedra. We also have chains, sheets, and three-dimensional networks. The three-dimensional networks being the most complex. So ferromagnesium silicates have magnesium and iron present in the crystal structure. They tend to be darker minerals, mostly gray and black. They have a compact structure, making them have higher density. Their densities usually range between 2.7 to 3.6 grams per centimeter cubed. Their average density is 2.9 grams per centimeter cubed. Ferromagnesium silicates are typically isolated chains and sheets of tetrahedra. Common examples include olivine, the pyroxene group, the amphibole group, and micas. The pyroxene group is represented by the mineral agate, which is shown in Figure B. And the amphibole group is represented by its most common member, hornblende, which is in Figure C, and the mica group is represented by biotite, which is the most common member in Figure D. Non-ferromagnesium silicates do not have magnesium and iron present in their crystal structure. They tend to be lighter in color than ferromagnesium silicates. They have a less compact structure, making them have lower densities. Their densities usually range from 2.6 to 2.9 grams per centimeters cubed. Their average density is 2.7 grams per centimeters cubed, which is 0.2 less than the ferromagnesium silicates average. Ferromagnesium silicates, non-ferromagnesium silicates tend to be 3D networks, sometimes along with sheets of tetrahedra. Common examples include the feldspar group, quartz, muscovite, and clay minerals. The clay minerals are represented by serpentine in Figure D. The isolated tetrahedra have a base chemical formula of Si silicon oxygen 4. All members of this group initially have a net charge of -4 because of the silicon having a +4 charge and each oxygen having a -2 charge. The silicon to the oxygen ratio is the lowest for isolated tetrahedra. The ratio is 1 to 4. The olivine group has a single tetrahedra that are connected by atoms of iron and magnesium. Olivine silicates tend to be any color in between olive green and darker colors like gray and black. They are darker when they have more iron. They are abundant in Earth's mantle and in iron magnesium rich igneous rocks. They tend to be in high density because of closely packed structures and large ionic structures. They are stable at high temperatures and pressures. Olivine crystallizes at very high temperatures and aren't very resistant to weathering. Primary occurrences in igneous and metamorphic rocks. The garnet group is like the olivine group in structure but not in composition. Single tetrahedra are connected by atoms of iron and magnesium, but can also include calcium, potassium, aluminum, and other elements. The range of colors including colors like red, purple, black. And they are usually high in density because of closely packed structure and large ionic structures like olivine. They are stable at high temperatures and pressures. They occur in igneous, metamorphic, and sedimentary rocks. Most garnet is found near the surface of the earth and forms primarily when high aluminum content on sedimentary rocks undergoes intense heat and pressure. There are two common forms of chains in the chains of tetrahedra group: single chain and double chain. The ratio for silicon to oxygen is 1:3 for single chain and 4:11 for double chain. The most common example for single chain is the pyroxene group, and for double chains is the amphibole group. The pyroxene group is the calcium, magnesium, iron silicates group, meaning that the chains are linked by the cations of these elements. The colors tend to be green, black, or brown. The chain of the tetrahedra is connected by sharing a single oxygen anion. The bonds between the silicon and oxygen are much stronger than the bonds linking the chain of the tetrahedra together, so usually there is a split between silicate chains, causing systematic cleavage pattern shown by two cleavage directions that are almost perpendicular with each other. Like olivine, it is abundant in the Earth's mantle. They crystallize at lower temperatures than olivine, but still at high temperatures. Occurrences mainly in the igneous and metamorphic rocks. The amphibole group is the set of silicate minerals that are complex. They vary highly in chemical composition: calcium, magnesium, iron, and aluminum silicates group, meaning that chains are linked by cations of these elements. Also, water is stored within the crystal structure. The bonds between the silicon and oxygen are much stronger than the bonds linking the chain of tetrahedra together. So usually there is a split between silicate chains, causing systematic cleavage patterns shown by cleavage directions at almost 60 degrees, approximately 60 and 120 degrees. They crystallize at lower temperatures than pyroxene, but still moderate to high temperatures. The most common example is dark green hornblende, occurrences mainly in igneous and metamorphic rocks. The sheets of tetrahedra group has a silicon to oxygen ratio of 2:5. The primary example of sheets is seen in the mica group. The tetrahedra are connected by cations. An example of mica is biotite, which is known for being the primary mineral on ocean floors. The cations for biotite are iron, magnesium, and potassium. The weak bond between sheets causes cleavage to be parallel to the tetrahedral sheets. This enables us to pry the crystals with some tool like tweezers. It also contains water in the crystal structure. Micas tend to crystallize at lower temperatures than the amphibole group. They occur in all rocks, including igneous, metamorphic, and sedimentary. Clay minerals have a similar sheet-like structure to micas. The three-dimensional networks of tetrahedra have a silicon to oxygen ratio of 1 to 2, and they occur in all rock types. The primary examples of these are quartz and the feldspar group. Quartz, the chemical formula for quartz is simply 1 silicon and 2 oxygen. Almost the entire quartz structure is made up of silicon and oxygen. Occasionally there'll be some impurities within the quartz. Oxygen anions connect tetrahedra. Quartz is unique because there is no cleavage. This is due to the strong bonding of the silicon and oxygen. It's most abundant on Earth's surface. It is very resistant to weathering and can survive water transportation. It has various colors including pink, green, purple, blue, and clear, as shown in A, B, and C. In feldspars, sometimes aluminum replaces the silicone in the structure, so tetrahedra is connected by calcium, potassium, and sodium cations. The structures include two cleavages with 90-degree angles between them. Typically, the feldspar has a white or pink color and a rectangular shape. The average density is 2.7 grams per centimeters cubed. Feldspars are split up into two types, plagioclase and potassium. Plagioclase minerals have an abundance of sodium and calcium and negligible potassium, while potassium minerals are the opposite by having an abundance of potassium and negligible calcium and sodium. Feldspars make the biggest portion of minerals on Earth, so we see them probably the most in our daily lives. The Bowen's reaction series shows us there is a relationship between the cooling of magma given a mineral and the complexity of their structure. Isolated tetrahedra are the least complex structure, which is the structure of olivine. Olivine crystallizes at the highest temperatures on the reaction series, and quartz crystallizes at the lowest temperatures. Quartz also has the most complex tetrahedra structures or networks. There is a pattern of complexity of tetrahedra increasing for lower crystallizing temperatures. Also, weathering is least effective on more complex structures of tetrahedra. It is important to understand silicate rock-forming minerals because they make up most of the ground that we walk on and the ocean floors. If we didn't know what minerals would be best to build on, we would have our homes and buildings falling apart because the foundations they were building on are susceptible to weathering, for example. It is something we don't commonly think about, but it is crucial for the busyness of construction in our society today.